In the last video, I explained some basic concepts, how vacuum tubes work, and the basic concept of the grid, which we will now call the control grid, and its role as a valve in the tube's design. So if you're not familiar with these concepts, check out the previous video. Moving forward, we will now consider how the basic bias concept from the previous video relates to the concept of a load, with the tube's unipolar type conductivity and elements needing charge to non-zero voltages for operation, especially the plate needing a strong positive charge to attract the free-floating or negative space electrons in the vacuum. We need current to these elements to achieve that. As such, some amount of electrical current must be present, whereas in a computer we might think of shifting wave symmetry as a logical process. In an analog design, it requires the potential for physical force or energy to accomplish this. So let's think of our signal as this fellow on a surfboard, coasting along to the peaks and troughs of our signal. To amplify this signal through a vacuum tube, we need to build up this bigger wave for our surfer to ride on. Now we can more clearly see the peaks and dips, but it's still all riding on top of this big wave. So if we want to remove the wave to be left with just these new groovy moves, we need something to absorb that energy, moving from a current amplifier to a voltage amplifier. And there are tons of other things we could look at or expand on here, but I think this knowledge will be adequate for understanding the following information in this video. And I'll include some links in the description with more in-depth concepts from a more traditional electronics engineering standpoint for like amp repair and design, if you'd like to explore all of this a bit further from that approach. Now, expanding on the brief intro to bias excursion in the previous video, while I wanted to focus on how bias excursion relates to DC offset, I didn't want to be misleading when I used the word sag. So now that we have this basic load concept, it's important to differentiate that this sag that is happening during the bias excursion is actually the signal being pulled more negative, and we will see more of why this is as we talk about clipping. While it might be easy enough to just extrapolate some type of asymmetrical distortion from this wave sort of sagging through the device, even if the transfer was completely linear, I did perhaps gloss over some more fundamental components of the tube's clipping behavior, things that further enhance this asymmetrical output concept, and I will cover some of those now. The positive half of the signal is susceptible to grid clipping, while the negative half is susceptible to cutoff clipping, and we will talk about the latter first. If we think now of the control grid as the voltages it contains relative to the plate and electrons, and how it's the positive and negative charges that operate this valve to control the flow of electrons, we can see the unique problem with the negative portion of the signal. As the control grid becomes more negatively charged, it starts to not only restrict flow, but slow down flow as well, until the charge is so great that it repels the electrons altogether. And this has a unique shape as we slow down to that absolute zero clipping point. On the positive side, as the control grid becomes more positive, it ceases to have any meaningful impact in restricting flow. It can't open up anymore. So any further increase to the control signal has no impact on the output. We've hit the ceiling, so to speak, and this behavior is much more linear with a more hard kind of clipping at the maximum. So I hope we can kind of see the imprecision in these devices comes from an inability to isolate these electrons to do only what we want without some other impact to these fluctuating charges. And it also has a reciprocating effect where the buildup of electrons, like in the steam analogy, start to impact the integrity of the other elements. And the electrons weighing down with a negative charge is the essence of the bias excursion. And there's really so much more that we could cover here, but I think this is a good kind of basic grasp of what's going on. But now I want to shift to Tetrodes and Pentodes, because this is directly related to the flaws we see with triodes. To improve linearity, precision, and output frequency and range, the fourth element we add to this equation is called the screen grid, and it attempts to correct the flaws in triodes by using a positive voltage, lower than the plate, but higher than the other elements. And it directs, jumpstarts, beams, or otherwise encourages the electrons to move in the direction of the plate, discouraging any loitering around here by the control grid. And this design works well, really well in fact, too well. Boosting these electrons causes them to move so fast now sometimes that they hit the plate so hard and bounce back off of it. And some bounce so hard, they end up being more attracted to the screen than the plate. And this causes a unique disruption to the load where it alters the operating conditions and by effect the transfer curve of the tube dynamically. But it still gives us greater precision, which can give us a greater range of power. And Pentodes expand on this concept with one more grid, the suppressor grid. The suppressor grid sits between the screen grid and the plate, and sits at a relatively negative potential. The idea is that the screen grid will project the electrons right through the suppressor grid, and then the suppressor grid will repel any electrons that bounce back off the plate to encourage them to stay closer to the plate than the screen. And this also improves efficiency, but at the end of the day they still suffer from the same issues as triodes and tetrodes, just to a lesser degree. Tonally, we could generalize triodes to have more asymmetry and earlier breakup characteristics, while pentodes may be more linear with a harder onset of distortion. But all tubes and designs are different, so this is really an oversimplification. This is obviously still only scratching the surface, and I look forward to going into maybe more specific things later as I look at more tube-based designs for software. But Big Bad Tube has been overhauled to version 2 now. Free for those who own version 1 and definitely worth checking out again if you passed. While it looks and operates mostly the same, the entire underlying design has been reimagined. A lower overall gain structure that attempts to make use of a wider operating range within the selected tubes. As such, less crushing distortion and more nuance to really bring out and accentuate the physical properties that were discussed in this video.
Life is a game, only the rich can survive, while the rest of us are stuck here paying for their crimes. So I'll be pitiless until the day that I die, anticipate without a trace, no matter how hard I try.